Okay, welcome back. We are going to look at subsection 2 of 1.6, bases for column and row spaces. Or should I say spaces? No, no, I should not. Bases for column and row spaces. So we've got this example here. We've got this matrix F with these 5 columns, and it is in reduced echelon form. And what the question says is explain why the 3 pivot columns make a linearly independent list of vectors, and why the column space of F is equal to the span of just those 3. Why you don't really need the non-pivot columns 2 and 5. Now, this is pretty easy to explain looking at just this one, but what I want to do is explain why this concept works in general, because it's going to help justify a theorem below, theorem 1.16, 1.16. So let's look at that real quick and then look at example 8. Okay, so theorem 1.16 says a basis for the column space is the pivot columns of A form a basis for the column space of A, which is exactly what example 8 is asking you to show. So A, it turns out, is row equivalent to F from the previous exercise, which you can check if you want. And that means that the pivot columns of A are in those spots: row 1, column 1, row 2, column 3, and row 3, column 4, like so. And so what the theorem says is that this list of 3 pivot columns should make a basis for the column space of A. And that's what this is asking us to show, that it's a linearly independent list that spans the column space. So that's what we're going to try to do. That's where we're going with this. And like I said, I want to try to explain why the pivot columns are linearly independent in general, especially when it's already in reduced echelon form, and why the column space of a reduced echelon form is equal to the span of the pivot columns, not just in this particular case. So first of all, when looking at A, what you notice about the pivot columns here is that because they're in reduced row echelon form, each of them has a 1 as the only non-zero entry in its column. And because every pivot is in a different row and a different column from the others, because it's, you have the whole staircase thing, that means that each of these 3 columns has a 1 in a different spot than the other ones, like in a different row than the other 3 pivot columns, and everything else is 0. And that's true for any reduced row echelon matrix. So that means there's no way to get any one of them as a linear combination of the others. Because for example, any linear combination of the first 2 pivot columns cannot give you a 1 in position 3. So that's going to make it so none of them is a linear combination of the others, and that gives you a linearly independent set by theorem 1.6. Theorem 1.6 is the characterization of linear dependence. Okay, so we got that. Let's look at part B, which says explain why the column space of F is equal to the span of just these 3 columns. Well, the definition of column space in general, it's the span of all 5 of the columns. Why is it that if you remove 2 of the columns, these non-pivot columns, that you will get still the same span? Well, that's actually exactly what theorem 1.5 says. Removing dependent vectors doesn't change the span. So if you can get one of the vectors as a linear combination of the other vectors, removing it doesn't change the span. So we just need to show that column 2 and column 5 are linear combinations of the others. And you can see that here, that like negative 5, 0, 0, 0 is, you get that by doing negative 5 times the first column. So that is a linear combination of the pivot columns. But this works in general because I'm kind of giving a proof of theorem 1.16 by way of this example. So like not just this matrix, but any reduced echelon matrix, the non-pivot columns, you're going to be able to write them as a linear combination of the pivot columns for the following reason. So if we think about where, in general, all of the non-zero entries of the non-pivot columns are, I have them highlighted in green here. They are always going to be in the same row as a leading 1 in a pivot column, because if there wasn't, if you had a non-zero entry in the bottom right here, and there was no pivot to the left of it, no leading 1 to the left of it, then this would be the leftmost non-zero entry, and it would be a pivot. So every non-zero entry that is not a pivot has a leftmost non-zero entry to the left of it somewhere in the same row. And you can always you can get this 6 by doing like 6 times this column with just a 1 and a bunch of other zeros. And so you could do 6 times column 1 plus 7 times column 2 plus 8 times column 3 and add those together, and you can get all the non-zero entries that are in non-pivot columns, like so. So that's why in general, the non-pivot columns of any reduced row echelon matrix can all be written as linear combinations of the pivot columns. Okay, and that means that you can use theorem 1.15 to remove them without changing the span. All right, so that shows why the pivot columns of F in reduced row echelon form a basis of the column space of F, because they're linearly independent and the pivot columns span the column space. But what the theorem says is that the pivot columns of any matrix, even if it's not in reduced row echelon form, are a basis for the column space of that matrix. So, for example, here's A, which can be shown to be row equivalent to F. So that tells us where the pivot positions in A are, like we said, here, here, and here. So for part A, to show that this is linearly independent, I want to do this in kind of like a straightforward way, just to show that the only solution of the homogeneous equation is the trivial solution. So let's do that. So we're assuming we have a solution x1, x3, and x4 of this homogeneous equation. We want to show that it must be 0. And we know that this homogeneous equation can be written as a system of equations with this augmented matrix, like so. And we also know that because A is row equivalent to F, that whatever sequence of row operations that could reduce A to F is going to reduce columns 1, 3, and 4 to columns 1, 3, and 4 of F. And we know that the only solution of this system of equations that this represents is the trivial solution, because F1, F3, and F4 are linearly independent. And we also know that this system is equivalent to this system, not just row equivalent, but also it has the same solution set because we did Gaussian row operations to get them there. So, yeah. So that shows that we have got that. Let's explain why the column space of A is equal to the span of A1, A3, and A4. So we're going to make basically the same argument as before with part B, because we know from part B that all of the non-pivot columns are linear combinations of the pivot columns, right? Now, I'm going to claim that that same relationship is true amongst the columns of A, and then explain why. Like, for example, what I'm claiming is that column 2 of A is negative 5 times column 1, and column 5 of A is 6 times column 1 plus 7 times column 3 and 8 times column 4. And why? How do I know this? I mean, we could actually just like check with this example. I mean, at least with the first one, it's pretty easy to check that the second column is negative 5 times the first one. But why does this work in general, that the non-pivot columns of any matrix A are going to be some linear combination of the pivot columns? And why is that? Well, because the fact that A2 equals negative 5A1 gives you a solution of the homogeneous equation. And that solution is 5, 1. Well, let's write this out. It is 5A1 plus A2 plus 0A3 plus 0A4 plus 0A5. That has got to be equal to the 0 vector. Just all I did is I added the 5A to both sides of this. And that means that 5, 1, 0, 0, 0 is a solution of the system with the augmented matrix, like so. And that system is equivalent, like we just did here, to, because this is basically just A augmented with 0, that is equivalent to F augmented with 0. And so 5100 is also a solution of this system, and which is what we already know. So since 510 is a solution of this system, we can say it's also a solution of this system, and it also makes this here. So we're kind of doing the logic backwards, but I think it works fine. So here it is with the logic written out in maybe a slightly more formal way. So yeah, and by the same reasoning as this, 6, 7, 0, 8, -1 is a solution of A0. Using the same logic, we can say that this is also true. So all of this is to show that A2 and A5, because they're equivalent to non-pivot columns of F, A2 and A5, because they are non-pivot columns of A, must be linear combinations of the pivot columns. So we can again use theorem 1.15 and say we can remove them without changing the span. And so the span of all of them, which is the column space, is equal to the span of the fewer vectors after you remove the ones that are linear combinations of the others, like so. Okay, so that is basically a proof of theorem 1.16, but using a specific example to illustrate it. But the same logic works in general. There is a more formal proof in the book if you really want to read it, but you don't have to. One thing we should say about this is that this does not say anything about the pivot columns of an echelon matrix equivalent to A. It doesn't say anything about the pivot columns of F being a basis for the column space of A. And if you think about it for a second, you can see why they really are not a basis. Let's look at it. Okay, why is that? If you think about the span of these three vectors, notice that they all have a 0 in the bottom row. But when you look at column A, the column space of A includes multiples of this vector and this vector, which do not have a 0 in the bottom row. So the column space of A definitely contains vectors that are not multiples of the pivot columns of F. So you got to take the pivot columns from A itself, not from another matrix that's row equivalent to A. Okay, so that's my one little warning. I guess the reason I'm saying this is because it's confusing, because the next theorem works the other way. When we talk about rows, we actually are going to get the rows of the echelon matrix. So it's easy to get that mixed up, and I will not judge you if you do. Anyways, let's look at the row space in the next video. I will see you then. Take care.